Hi, welcome back. Today we're going to be looking at what we call the concavity test of a function. It's very similar to the first derivative test, in which case we're going to be looking for the signs of a function. So let's take a look up here. Before we start, let's review the first derivative test. So down below, we are given the graph of the first derivative. We want to use sign charts to determine where the function is, 1, increasing, decreasing, and has any relative maximums and minimums. And we do want to justify. So if I were to take a look here, of course, our first thing we have to do is we have to find out our critical numbers. And we should remember the critical numbers are where the derivative is 0 or d and e. And I can calculate that pretty easily. In this case right here, remember this is the graph of our derivative. So we know that the derivative is positive above the x-axis and that the derivative is negative below the x-axis. And on the x-axis, we know the derivative is 0. So that gives us our critical numbers, which are going to be -2 and 1. Draw your sign chart. Sign charts are very important for us. F prime and F. And this is going to give me -2 and 1. We don't have any domains on here, so we're just going to maybe assume forever, never, never. So let's see here. We want to find out before -2 is the function, is the slope positive or negative. That's what we're looking for. We're looking to see if the slopes are positive, so we only want to look at their signs. And since before -2 we're below the x-axis, we know the slopes of the function are negative, which means that our function here is going to be decreasing. Between -2 and 1, same thing. We're still below the x-axis, so it's going to be negative. So it's still going to be decreasing. And after 1, of course, is positive because we're above the x-axis and our function here is increasing. And now we can answer everything. We can say f is increasing, and we can say on the domain 1 to infinity, and that is because the derivative is positive. F is decreasing on the domain -infinity to -2 or -2 to 1, and that is because the derivative is negative, is less than 0. And we want to find out any relative max or mins. We don't have a relative minimum because the slope, we don't have a relative maximum, excuse me. Remember, for a maximum, you have to go up and then down. For a minimum, you go down and then up. We do have a relative minimum, but there are no relative maximums. So I'm going to go and say that f has no relative maximums. Remember, spell it out, relative max. Next, we do have a relative minimum. We can say f has a relative minimum. Whoops, can't spell relative right. A relative minimum at x equals 1. And that is because the derivative goes from negative to positive. And that's what we want to say there. So the second derivative, or concavity test, is kind of the same thing. So today we're going to take a look at the second derivative of a function, f double prime. The second derivative relates to the change in the slope of the graph. As the slope so if we take a look at our graph up here, as the slope is changing, notice we are like for here, we are changing. If our slope goes from, it's a positive and it's going to a negative, what we say is that the slope is changing here, we're going to get something called concavity. In other words, the second derivative lets us know where a function is opening up and opening down. So let's review real quickly. The function f, this finds the y value at a particular x point. That's the function point. The derivative finds the instantaneous rate of change of the function at an x value. We can also use to find out where the function is increasing, decreasing, and relative max and mins. This was our first derivative test. Right there. The concavity, this is what we use to find where a function is opening up or opening down. So let's see if we can look at like an example right here. Here we have the graph of f of x equals x cubed. If we were to take the second derivative, we would get 6x. So we can compare the graphs below and see what we know. So we graph so here we have f of x in red for me, and in green we have, or the line, that is the second derivative. And we want to compare the two. So let's see. If the function f of x is opening up, remember, what does opening up look like? That's concave up. It looks like so. So after 0, it looks like it's opening up here. Well, what does that tell us about the sign of our second derivative? Is it above 0 or is it below 0? Well, if we take a look at the concavity, at this point right here, the second derivative is above the x-axis. So if this was my second derivative graph, we're going to say that this is positive, just like we did for the first derivative test. Remember, for the first derivative test, we said if we're above the x-axis in our derivative graph, we're positive. Same thing here. Here we have the graph as being concave down. Well, look at the line. We're below the x-axis. So that's telling me that if the function opens down, oh my gosh, spell check did not catch that one. If the function's opening down, then we can say that the second derivative is less than 0. So let's go ahead and give a more formal definition of concavity. If f is a twice differentiable function, then we can say the following. F of x is considered concave up if the second derivative is positive. Now, another way to look at concave up is we say that the slope, that the derivative is increasing. If I look at a function that's concave up here, if I go along this line, notice I'm going from a negative slope to a positive slope. So we go from a negative slope, where the slope is 0, to a positive slope. Notice the slope is increasing, and that is actually a more formal definition of what it means to be concave up. You don't have to know that to master this material, though. Likewise, if a function is concave down, we said the second derivative is less than 0. Well, that's telling us that here I'm starting off at a positive slope, and I'm going towards a negative slope. We say that the derivative, or the slope, is decreasing, because we're going from a positive slope, the slope is 0, and then we go to a negative slope. So we call that concave down. Now, most graphs, like an x cubed graph, could look something like this. Notice, we have one part that's concave down, opening down, and we have another part that's concave up, or what we say is opening up. Somewhere in the middle, it's going to change. And this has a special name for it. This is what we call a point of inflection. If the function is twice differentiable, and the second derivative changes signs, remember, if it changes signs, we're changing concavity. So therefore, f changes concavity. It's going to go from concave up to concave down, or concave down to concave up. This is what we call a point of inflection. There has to be a point of inflection. Where they change concavity is what we call a point of inflection. And we kind of see that in the graph here. If we look at the graph to the side, at x equals 1, the concavity is changing from opening up, to concave down, or opening down. So this is what we call a point of inflection, or we call it a POI. You can call it an IP as an inflection point as well. Now, notice we're looking at the signs. If it's concave up, here we're saying that the second derivative is positive. Concave down, we're saying the second derivative is negative. At some point, what would this value of the second derivative have to be? If you get 0, you're pretty darn close, because that's right. If I'm going from a positive to a negative, at some point we have to cross 0. So that's how we can find a POI, one of the first ways to find it. So what we're going to do is we're going to find these, what we call these possible points of inflection. And that's what we're going to call these, a possible point of inflection. Now, a possible point of inflection is nothing more than where we're going to look at the second derivative. Remember, we said it has to go from a positive to a negative, so we're looking for whether the second derivative is 0. But like candidate's test, or the first derivative test, this could also be a D and E for us. We'll talk about that later too. Notice, this is oddly like our critical numbers. This is like our first derivative test. We don't want to call them critical numbers because that's really only typically established for the first derivative. So we call these PPOIs instead, possible points of inflection. So let's take a look at how we do this, the concavity test. For a twice differentiable function, in other words, we can take the derivative twice, we're going to find where the second derivative is 0 or D and E. And again, we call these possible points of inflection. Next, we're going to draw a sign chart, just like we did for the first derivative test, and we're going to test each region for positive or negative to determine the concavity. So let's take a look. Here we are given the graph of the second derivative. So we know that this is f double prime of x. Discuss the concavity of the function and also find any POIs, and we're going to justify. We're going to be back to our sign charts again. So the first thing we have to do is we have to find those possible points of inflection. Papoi. And that is where the second derivative is 0 or D and E. Now, since we're given the graph, it's not going to be a D and E. Now, just like the first derivative, if we're above, we are saying that the second derivative is positive. Below, the second derivative is negative. And on the x-axis, that's where the second derivative is 0. Very easy to do. Nothing really new for us. So I can find those. Well, where is the second derivative 0? Negative 4 and negative 2 and 3. Doing our sign chart. Again, we're going to pretend like this goes on forever. Oh my gosh, I didn't recognize it. It's the Wornow function. Looking at our second derivative, and then we're going to take a look at what's it make my function look like. Whoops, sorry about that. Plug in your critical numbers. Negative 4, negative 2, and 3. And we just use this. Ready? Before negative 4, look, we're above the x-axis. That is telling me that the second derivative is positive. Now, in the first derivative test, we said drawing up, going up. But in the second derivative, we're talking concavity. So we're going to show concave up. Well, what does concave up look like? It looks like a U. So it's going to look like this. That's concave up. Between negative 4 and 2, we're below the x-axis. So it's negative. That's concave down. Between negative 2 and 3, we're above. And that's telling us that the concavity is positive. So we're going to be concave up. And between 3 and forever, positive. It's above the x-axis, concave up. So I can say f is concave up on the domain where it's positive, negative infinity to negative 4, or negative 2 to 3, or 3 to infinity. Remember, we want to break it up. Remember, always use soft brackets. They're the easiest way to use. Because the second derivative is positive. We can say f is concave down on the domains negative 4 to negative 2, and I think that's it. And that is because the second derivative is less than 0, just like first derivative test. But now let's take a look at our POIs. For this, we only want to find the place where it changes. And take a look. Here, it changes. I'm going from concave up to concave down. At negative 2, it changes. We're going from concave down to concave up. Notice, does not change at x equals 3. Stays concave up on both sides. So when I list out my POIs, I'm going to say there are POIs at x equals negative 4 and negative 2, and that is because the second derivative, we should put this as 0, and changes signs. That's all you have to put. Okay? Keep it simple. We just want to make sure they change signs. And there's your answer. Each piece of cake. All right, go to the next video. We'll take a look at a few more examples. I'll see you then.